Hello everyone. For this video we're going to be taking a look at something slightly different than what we've done for the last couple videos. In those last couple videos we were looking at angles in circles and their corresponding intercepted arc measurements. But for this video we're going to be looking at lengths of segments. So not so much about angles in this video, but we're looking at lengths of chords, like lengths of secant segments, and lengths of tangent segments. So let's jump right in. There are three theorems that we're going to be learning in this section, so let's run through those really quickly and then we'll take a look at how they might apply in some example problems. So to start off, we have theorem 9-11, and it says that when two chords intersect inside a circle, the product of the segments of one chord equals the product of the segments of the other chord. And of course we remember that product is the result of multiplication. So let's take a look at what this is saying about this diagram right here. In this diagram you can see we have two chords. Segment DB is a chord and segment CE is a chord. They are intersecting inside a circle. So this diagram is kind of what we're talking about, obviously. And so according to the theorem, the product of the segments of one of the chords. So let's look at chord DB. Its two parts are DF and FB, and the product of those would be DF times FB. So that product equals the product of the segments of the other chord. So if our other chord is CE, then the two parts of that are CF and FE, and so if we multiply those together, CF times FE, it should equal the DF times FB. So in other words, if we were going to put some numbers to this here, if we said that maybe this was 3 and this was 8, and let's say that this was 4 and this is something we're trying to find, what we could do using this theorem is we could say that 3 times 8 would equal 4 times x. And so that would simplify and would give us that 24 equals 4x. And then dividing each side by 4 would tell us that in this case x would be equal to 6. So that one's pretty simple. Not too complicated there. In theorem 9-12, we're going to introduce this idea of secant segments. And so what theorem 9-12 says is that when two secant segments, so in other words that would be a segment that intersects a circle in two places, like segment CE intersects this circle at B and at E, but both of those are not the endpoints of this segment. Only one of them is an endpoint of segment CE, so that's what a secant segment is. When we have two of those drawn to a circle from the same external point, then the product of a secant segment and its external segment equals the product of the other secant segment and its external segment. So what's the external segment part? Well, if CE is a secant segment, then CB is what we would call an external segment. It's the part of the secant segment that's outside the circle. You can see the part EB, that part of segment CE, it's inside the circle. Part BC, segment BC, is outside the circle. So that's called an external segment. And of course that would mean that this would also be an external segment as well. Segment CG would also be an external segment. So what is this theorem telling us about this picture? Well, it tells us that if I take the whole secant segment, so it would be CE, and I multiply it times the length of just the external part, BC, I can do the same thing with the other secant segment. I can take its entire length, or CF, and multiply it by just the external part, CG, and these two products should be the same. So if I were going to throw a few numbers on here, let's say they'll say this was, let's say that was 12, and this was 10, and let's say that's 11, and that's x. So what do we have here according to theorem 9-12? Well, we would say that the length of CE, which of course is going to be 12 plus 10, times just the external part, which would be 10, that would be equal to the length of CF, which we can express as x plus 11, times just the external part, which is 11. So now if I clean this up a little bit, I would have 12 plus 10, which is 22 times 10, equaling, and then I can distribute right here, 11x plus 121. So that would mean that 220 would equal 11x plus 121. And then I could subtract the 121 from both sides, and that would say that 99 equals 11x. And that would mean that x is, of course, going to be 9. So that's how we could set up a problem using theorem 9-12. The next theorem, 9-13, it kind of builds off of what theorem 9-12 tells us. It says that when a secant segment, let me write that a little bit clearer, when a secant segment and a tangent segment are drawn to a circle from an external point, the product of the secant segment and its external segment is equal to the square of the tangent segment. So we can see in this diagram we have a secant segment JK, a segment that intersects the circle twice, and we have a tangent segment JM. That segment only intersects the circle one place. Even if we turned it into a line, it would only intersect the circle in one place. So they're both being drawn from point J, from this external point J. According to theorem 9-13, if I took the entire secant segment's length, that would be JK, and I multiplied it times the external part, which would be LJ, same idea as what we talked about in theorem 9-12, JK times LJ, that would equal the tangent segment squared, so JM squared. So if I were to throw some numbers into this picture to kind of get an idea of what we're talking about, if I said that this was 12 and this was 4 and this was x, how would we solve for x? Well, we would set this equation up, jk, which is going to be a length of 12 plus 4, times lj, which is just going to be a length of 4, equals jm, which is x squared. So that would be 16 times 4 equals x squared. 16 times 4 is 64. So if 64 is x squared, then x would be the square root of 64, which is 8. And so that's how we would apply theorem 9-13 to a problem like this. Okay, so here's 3 examples for you to try. Video is going to pause and you know what to do. Work these out, enter your answers, and then let's see how you did. Okay, so let's look at example 1a. This is using theorem 9-11. All right, this is theorem 9-11 because we have 2 chords intersecting. So all we're going to do in example A is we're going to take the 2 times the 6, the parts of this chord, the 2 and the 6, multiply them together, and that should equal the 2 parts of this chord multiplied together, which is an 8 times an x. So that'll be 12 equals 8x. So to get x by itself, I need to divide both sides by 8. So now I know that x is 12 over 8, which if I reduce that by dividing top and bottom by 4, I could get 3 over 2, or if I just typed in my calculator 12 over 8, it would tell me 1.5. And either of these answers would be okay. 3 over 2 or 1.5 or 1.5, any of those would be fine for that one. Now in example B, we would be using theorem 9-12 because we have 2 secant segments. So what we're going to set up, I might need a little more room here, so let me scoot it up. What I'm going to set up here is I'm going to say that this entire secant segment, which of course has a length of x plus 5, x part plus the 5 part, times its external part, which is just 5, should equal this entire secant segment, which is 9 plus 6 times its external part, which is 6. So I need to clean this up a little bit. First, I'm going to use the distributive property. I'm going to say that 5x plus 25 equals, and now this is going to be 15 times 6. So that means that 5x plus 25 equals 90. And then I'm going to subtract 25 from both sides. That'll leave me 5x equals 65. And if I divide both those sides by 5, I will get an answer of x equals 13. And then finally in letter C here, we are going to be using theorem 9-13 in letter C because you can see we have a secant segment and a tangent segment. So my equation is going to take the entire secant segment's length, and so that secant segment has a length of 4x plus x, right? The 4x part plus the x part. and that gets multiplied by the external part, which is x. And that gets set equal to the tangent squared. So now if I simplify or combine my like terms over here, that would be 5x that's getting multiplied times x equals 20 squared, which is 20 times 20, which will be 400. And now this turns into 5x squared, not 6x. Some people will accidentally make this 6x right here. Remember, if we take 5x times x, that results in 5x squared, and that equals 400. So now if I divide both sides by 5, then x squared is equal to, that should give us 80. And if x squared is 80, then x would be the square root of 80. And since 80 is 16 times 5, 16, that looks a little bit like 16.5. 16 times 5, then we can take the 16, and since that's a perfect square, its square root will come outside the square root symbol. So it'll be 4 square root 5. And let's see, what is 4 square root 5 as a decimal in case you did it that way? It would be about 8.9. So if you gave me a decimal answer, that would be fine too. It would be about 8.9. So there you have it. That's the last section in Chapter 9. Again, it's looking at segment lengths instead of angle measures like we have been. So good luck, and we will see you in the next chapter. All right, have a good one.